And so section 4 brings us to these additional topics in probability and counting. You may have seen these in one way or another in your Algebra 2 class in high school. We're going to begin with permutations. So a permutation is an ordered arrangement of objects. And the key word here is ordered. So order is going to matter here. And the number of different permutations of n distinct objects is this n exclamation mark. And the expression n exclamation mark should be read as n factorial. All right, that's what that exclamation mark is read as. It's factorial. And it's defined by n factorial is going to be n times n minus 1 times n minus 2 times all the way down to 3 times 2 times 1. All right, so you just take all the whole numbers that are less than n and that are greater than 0, and you just multiply them together to give you n factorial. Just for some examples, 0 factorial is kind of weird, but we take that to equal 1. And so if you did 1 factorial, that's going to be just 1. 2 factorial is 2 times 1, which simplifies to 2. 3 factorial is going to be 3 times 2 times 1, which gives us 6. And then 4 factorial is going to be 4 times 3 times 2 times 1, which is equal to 24. So these things get large really, really fast. For instance, 5 factorial, which is 5 times 4 times 3 times 2 times 1. If you throw that into a calculator, you get 120. So just 5 steps out, we're already in the hundreds. These blow up really, really fast and become very large numbers. But we'll look at an example. So the women's hockey team for the 2010 Olympics are going to be Canada, Sweden, Switzerland, Slovakia, United States, Finland, Russia, and China, for a total of 8 teams. And so we want to determine how many different final standings are possible, right? So that's going to come down to, you have 8 different teams for the first place. Then you have second place, there's 7 teams. Third place is 6, and that just keeps going, right? So you're ordering here, which this is just 8 factorial. And so if you use your calculator, you do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which will give you a total of 40,320 possible different final standings at the 2010 Olympics. In a graphing calculator, what you can do is you can go to Math, then hit the left button, and then go down to, I believe it's 4. And that'll give you the factorial option. But notice that, 5 factorial was only 3 digits. 8 factorial turns out to be 5 digits. So these things blow up really fast, and we have to figure out how to calculate them a little bit more efficiently than just throwing in factorials. And that leads us to permutations of n objects, where you take just chunks of r many of them at a single time. And this is a pretty common thing that we want to do. So out of n objects, you want to figure out how many possible ways there are to just take r of those n different objects. And the way to calculate these is you take n factorial, right? So the total number of permutations, and you want to figure out how many you can take that are only r in size, which amounts to dividing out all of the ones that are not r in size. So, for instance, we want to find the number of ways of forming 4-digit code in which no digit is repeated. So there is going to be 10 digits. We want the number of permutations where we only take 4 of those at a time. And if we use this definition, this is 10 factorial over 10 minus 4 factorial. And so what we'll do is simplify the parentheses first. And here's where one of the important calculations tricks comes into play. We're going to expand the 10 factorial. And then underneath, I'm going to expand the 6 factorial over here. So if you notice, 10 factorial has a copy of 6 factorial inside of it. And so we're going to just cancel these numbers all out. And we're going to be left with 10 times 9 times 8 times 7, which we saw to be 50, 40 from our very first section in this chapter. All right, so this is just a different way to get that number that we already saw. Let's say that there's 43 race cars or cats, whichever one you prefer, starting at the 2010 Daytona 500. We want to figure out how many ways can the cars finish first, second, and third. So out of 43 cars, we only care about the top 3. Right, and so we want to figure out how many different ways that this could happen. This, again, is going to be 43 factorial over 43 minus 3 factorial, which, again, always simplify the parentheses first. And then we're going to play that same trick. Instead of listing everything out for 43 factorial and for 40 factorial, we know that 43 factorial is 43 times 42 times 41 times, and then 40 times 39 times 38 and so on, which is the same thing as 40 factorial. And I'm not even going to expand out the 40 factorial in the denominator, because we know that those are going to cancel out perfectly. So that leaves us with 43 times 42 times 41, which gives us 74,046 possible ways of getting a first, second, and third finish. All right, so if you're, I hate to say it, but if you're gambling on the Daytona 500 and you know that there's 43 cars in the race and you're looking for a trifecta, so figuring out first, second, and third place exactly, you have 1 out of 74,046 likelihood of getting that correct. So it's a very low probability. But sometimes we'll see on the next page that certain permutations can't be told apart. And you'll see what that means on the next page. But you may want to order a group of n objects in which some of the objects are exactly the same. Because some of the objects are the same, not all permutations will be distinguishable. All right, and we'll see what that means on the next page.